Let's finish topic 4.3. We started with first and second derivative tests, but now we're going to look at concavity, which will show us everything we need to know about the shape of a curve. The ultimate goal of this is going to be able to sketch the curve, but we're really going to save that for section 4.5. Remember, the second derivative of a curve is just the derivative of a derivative, right? Take the derivative twice. If the second derivative is negative, then we say that the graph is concave down on the interval. And if the second derivative is positive, then we say that the graph is concave up. If we have a second derivative at a point that's equal to 0, and if f changes concavity at that point, like it goes from negative to positive or positive to negative, then that point is called an inflection point. Right, so before, remember I was saying, find the, maybe the critical numbers and whether they're maxes or mins, and maybe the intervals of increase or decrease. Now I could also say, okay, find the intervals of concavity, whether it's concave up or concave down, and whether there's an inflection point. Now remember, one thing before we start this problem, or we start these problems, remember that there are 4 types of curves that we can have on a graph. And which kind of curve we have is completely determined by their first and second derivatives. Remember, here we have a function that's increasing and concave up. Increasing and concave down. Right, notice that here it's sort of facing up. Here it's sort of facing down. Again, decreasing and concave down. Right, again, facing down. And then here, decreasing and concave up. Right, believe it or not, that is up, right? It's like a bowl. It's facing up, right? Happy face. Happy face, concave up. Sad face, concave down. Now we can answer these problems. This problem is quite difficult. Maybe we'll come back to this a bit later. You can also look at it in the book. This problem, not quite as bad, but still a bit of messy differentiation, right? I mean, look at that quotient rule. Taking the second derivative of that, gross. Let's start out with example 3. Okay? Let's sketch the graph of h of x, right? Maybe roughly. But in doing so, let's find all of the information about critical points, intervals of increase, decrease, maxes, mins, concavity, inflection points, right? So what we're going to do, we're going to take the derivative set equal to 0, do our first derivative test stuff, then take the second derivative set equal to 0, and then find our inflection points and intervals, okay? So we're going to let h prime of x equal 0, right? Well, h prime of x, we know, right? We know that that equals 0, right? So it's just a matter of solving for x. Now, maybe you can eyeball that if x equals 0, then we're in the clear. But there is another point, believe it or not, right? If we factor out the 5, we get x plus 1 to the 4th minus 1 equals 0. Now, you can multiply all that out if you want. It's not the worst thing in the world. But you can actually be a bit clever and factor it out. You can actually write this as x plus 1 squared minus 1 times x plus 1 squared plus 1. And that all equals 0. Actually, let me just switch the pluses and minuses. Right? Because this is all greater than 0. So that's never going to be an issue. So this is going to be 5 times x plus 1 squared plus 1 times, and then let's just do this out, right? I'll just show you. This over here is going to become this. X squared plus 2x plus 1 minus 1. It simplifies nicely. just to be clear, all this nonsense we don't really care about, times x times x plus 2 equals 0. So anyway, this all implies that x equals 0 and negative 2. Okay? A little bit of algebra right there, right? Anyway, instead of doing the chart right now, I'm going to go right to taking the second derivative. You'll see why in a sec. Right, so the second derivative is going to be 20x plus 1 cubed. Right, we do the chain rule with the derivative is 1 equals 0. That's a bit more easy to see that x has to equal negative 1, and that's it, right? Divide by 20, take the cube root, done. Now we draw our interval chart. Now, instead of having just f prime, I'm going to have both f prime and f double prime here. I'm going to have all the critical numbers, which we know are negative 2 and 0. And here I'm going to have negative 1, right? Now, where am I coming up with these numbers? These are my critical numbers. And that was my possible inflection number. So let's see. When you plug things in, we plug things into h prime. Now, it's probably best to plug it into here before we start simplifying everything. If you plug in a number like, I don't know, negative 5 or something, you can see that we're going to get a big positive number. Plug in a number like negative 1, you can see we'll get a negative number, and plug in a big positive number, even just like 1, we'll get positive. Here, if we plug a number into h double prime, right, the second derivative, if we plug in like negative 2, just note that we'll get a negative number. Plug in a positive number, we get a, or not even a positive, plug in a number bigger than negative 1, we get positive. Right? So now we just write all of our information. Okay? So we'll just say f is increasing on negative infinity to negative 2, union 0 to infinity, and decreasing on negative 2 to 0. With local maximum, that's going to be f of negative 2. And then it goes, I think it's at negative 7, is it? Right, negative 2, yes. Oh, no, it's 7, positive 7. And local min, f of 0. Does everyone see why we have a local max and a local min? What's f of 0 going to be? 1 minus 2? Negative 1? Right. So baked in there are our critical points, right? F is concave up on negative 1 to infinity, and concave down on negative infinity to negative 1. With, and note that we do have an inflection point here, because not only is the second derivative 0, but f changed concavity, in this case from negative to positive. I guess I should say negative 1 comma f of negative 1. What's f of negative 1 gives us 3. Yeah, 3. Okay. I think we answered all the questions, right? Yep. So that's how you do that one, right? The others, little bit nasty. let's see what we can do. First of all, this one I'm going to just say try it, because this is nasty. But maybe we could do this guy, right? Again, this is a bit more involved than I'd give on a quiz or an exam, but it is something we should know how to do. Take the derivative, set it equal to 0. Take the second derivative, set it equal to 0. So let f prime of x equal, so let's see, it's going to be low d high minus high d low all over low squared. And we're going to let this equal 0. But before I write equal 0, let's simplify this a bit first. It's going to wind up being, let's see, the 2x, I'm just going to sneak an extra line, right? It's going to be 2x cubed plus 8x minus 2x cubed plus 8x all over this nonsense. Right, so notice that cancel, 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 and we wind up getting 16x over x squared plus 4 squared, right? Let that equal 0. Well, I think it's pretty clear, number one, that f prime of x always exists, right, because the bottom is always positive, and that f prime equals 0 at 0. Okay, good. Now, instead of drawing the interval chart at this point, I'm going to just go right into the second derivative and then do the interval chart where it's f prime and f double prime. Okay? So at this point, now let f double prime of x equal 0. This is going to be a little bit more involved, right? Just because we have a little chain rule in here, right? Maybe move this down a little bit, right? Just a little bit, right? Okay. So, low d high minus high d low. A little bit of a chain rule. All over low squared, right? Now this one's kind of cool, actually. If you notice, we have a factor of x squared plus 4 in each term on the top. So I can actually cancel like that, and so I'm going to. We normally don't get to do that with the quotient rule, but this time we do. And that's very nice, because simplification is going to be annoying, right? Here it's not so bad. This is going to be 16x squared plus 64 minus 6, no, wait, hold on a sec, minus, it's 64x squared all over x squared plus 4 quantity cubed. And if we simplify this a little bit more, we're going to get 64 minus 48x squared all over x squared plus 4 quantity cubed. And we want to let that equal 0, right? Lovely, right? But it's actually not the end of the world, right? Again, we know that x squared plus 4 cubed is always positive, so we really don't care about that so much. So we're going to find when just the numerator equals 0, right? We care only about the numerator. Right, and that's not quite so bad. You can divide by 16, and you get 4 minus 3x squared equals 0. You can actually factor that. Not sure how obvious this is. Right, so that's what you get. Believe it or not, that works. That factors, right? Try foiling it, okay? Right, so f prime of x, or sorry, f double prime of x equals 0 at x equals plus or minus 2 over root 3. Okay. Whew. So now let's draw our interval chart, right? The graph for f prime is not going to be that bad. For f double prime, be a little more involved. If you don't like writing 2 over root 3 or negative 2 over root 3, you can write it as 2 root 3 over 3, negative 2 root 3 over 3. Let me just write that here in case you're one of those guys who likes to rationalize the denominator, which is always good form. All right. So anyway, let's plug away. If we plug a number into f prime of x, right, I think we see if we plug in a negative number, then we get a negative derivative. Positive number, positive derivative. And now for the second derivative, a little more involved, but again, let's look at this guy. If we plug in a like negative 10 or something, we're definitely getting a negative on the top, right? That's a big negative number compared to that. And the bottom is always positive, so we're getting a negative. Plug in 0, we're going to get a positive. And here, plug in a number, we get a negative. Okay. And at this point, we just want to write down the information. I should point out, I didn't sketch the curve in the last problem. I'm not really concerned about that yet. We'll do that more in section 4.5. However, we know the shape of the curve, and we have a couple of points to work with. So we could get a pretty good sketch of the curve with this information that we're about to write down. We're still going to save that for section 4.5 when we focus a little bit more on a couple of points as well as asymptotes, right? Long-term behavior. Anyway, to finish this problem, we can say f is increasing on 0 to infinity and decreasing on negative infinity to 0. And it looks like we've got local minimum f of 0 equals, I think it's negative 1, right? Because we've got, 0, plug 0 into that, right? F is concave up on negative 2 over 3 to 2 over 3. And concave down, really everywhere else, right? There. And I guess we could say it does have 2 inflection points. Negative 2 over root 3, and I think it winds up being the same, right? You're squaring it, so it doesn't even matter whether it's negative or positive. You wind up, what is this? 2, so it winds up being 4/3 minus 4 over 4/3 plus 4, right? So 4/3 minus 12/3, right? So you get negative 8/3 over 16/3. So they both wind up being negative 1/2, I believe. All right, so that's what it is.